Hello, and welcome to my talk about the sequence of non-detectable, non-quasi-positive braids. My name is Elaina Aceves, and I'm a graduate student at the University of Iowa, and I would like to thank the organizers for giving me the opportunity to give this talk. Before we get started, I wanted to describe the motivation for this talk. So Jesse Hammer, Tetsuya Ito, and Keiko Kawamura were able to prove that all the knots up to 12 crossings have been classified up to positivity, by which I mean quasi-positive or non-quasi-positive, except for two knots, which are 12N239 and 12N512, which I've shown you below. Now, from my own research, I know that Plemenevskaya's psi invariant from Kobanov homology and Osvath and Szabo's theta-hat invariant from knot floor homology both fail to detect these knots. What I mean by that is that we suspect that these two knots are non-quasi-positive, but when we use these invariants on these two knots, they're non-zero, which doesn't tell us anything definitive about whether or not they're quasi-positive or not. So I wanted to show how ineffective these two invariants are in this specific, for these two knots, by finding a sequence of braids whose closures are non-quasi-positive knots, such that all of them in the braid sequence are not able to be detected from these invariants. So let's begin with some definitions. We have the braid group Bn, which the n is the number of strands that we use to create the braid. And this braid group is generated by what we call the standard generators, which is sigma 1 to sigma n minus 1, with the following two relations. Now I just want to make sure that we really get a handle on the sigma I, which is depicted below. Notice the I plus first strand travels across the ith strand, and that the ith strand is underneath. All of the other strands are unaffected, and they just have that orientation moving from left to right. If we wanted to look at sigma I inverse, on the other hand, then the ith strand would pass over the I plus first strand. Now, I've mentioned quasi-positive already, so what's the definition? A braid is quasi-positive. It's a product of positive powers for some conjugates of the standard generators. And what I mean by some conjugates, I mean it's just some braid words, W1 to WK. So here, this beta, we have these W1, W2, all the way up to WK. In the middle here, we have standard generators, all to positive powers. So below here, I have this example, beta 1. Notice at first we might not see it's quasi-positive, but when I introduce these parentheses and really reinforce that we have sigma 1 cubed and here's sigma 1 cubed inverse, while the other two of the words have positive powers, we can see that beta 1 is in fact quasi-positive. Now a braid is non-quasi-positive if we can't find such a representation, if it's not quasi-positive. Now, if we consider the closure of braids, we have knots or links. In my case, we're always going to have knots. So for our definition, we're going to have that a knot is quasi-positive if it can be represented by a quasi-positive braid. So the example we saw on the previous slide, beta 1, if we consider its closure, which I denote by a hat here, we actually get the knot 10-1-2-6. So we've just shown that 10-1-2-6 is a quasi-positive knot. Similarly, a knot is non-quasi-positive if it can be represented by a non-quasi-positive braid. So what are some results that are relevant to the talk today? We know our Osvath and Szabo proved that for any transverse knot, we have the following string of inequalities. So we have the self-linking number is less than or equal to 2 times the tau invariant minus 1, which is less than or equal to 2 times the 4-ball genus minus 1. In particular, if K is a quasi-positive transverse knot, Hedden and Plemenevskaya have proved that that first inequality is in fact an equality, that 2 times the tau invariant minus 1 is exactly the self-linking number. So the braids, the sequence of braids that I'm going to construct, I hope fulfill this property, which is very important because it's acting as if it's quasi-positive when they are in fact not. So how do I create my braid sequence? I let n be any positive integer, and I have the following braid word for kn. So notice I have sigma 1 inverse 2n plus 3 many times, which is from here to here. We have a sigma 2, 3 sigma 1s, and a sigma 2. Notice that we only need 3 braid strands to construct this braid. So what are some properties about the braid sequence that I've just created? we can calculate the self-linking number, which I've mentioned in that known results slide. So the self-linking number equals negative b, the braid index, which is the number of strands that we use to create the braid. N plus is the number of positive crossings, and N minus is the number of negative crossings. So N plus also can be represented as the number of standard generators that we raise to a positive power. So for us, Kn, I've redone the braid word down here. We can calculate the self-linking number. It's negative 3 because we needed 3 strands. 5 because there's 5 positive crossings. So we have 1, 3, and another one here, totaling up to 5. And we had 2 n plus 3 mini negative crossings coming from all these sigma 1 inverses. So our self-linking number in total is negative 2n minus 1. So another thing that I've mentioned is that these braid sequence is non-quasi-positive. How do we know this? So if we look at the closure of the first 2 guys in our sequence, K1 and K2, and we look at their closure, as I said, we know that these are in fact 10.125 and 12n235 from the non-info database. More importantly, they're both non-quasi-positive. So since our sequence is constructed by just adding more and more negative crossings, which create a more and more hindrance of a braid word becoming quasi-positive, all of the braids in our sequence are non-quasi-positive. And furthermore, the more we increase in our sequence, the more and more non-quasi-positive these braids become. All right, next we're going to calculate the signature. This is actually a stepping stone to calculate the 4-ball genus of of the braids in our sequence. So I claim that the signature of Kn is in fact 2 times n. All of the proofs I'm going to do today are proofs by induction. I'm going to go into more detail for the base case and then demonstrate how this would be done in general. So to calculate the signature, first you need to find a surface that has your knot or your braid as its boundary. So we're going to find that. Then we're going to calculate the Seifert matrix, which involves linking numbers, which we're going to denote V1. Then we calculate V1 plus V1 transpose and look at the eigenvalues associated to that matrix. The number of positive eigenvalues minus the number of negative eigenvalues gives us the signature. So as I said, let's go through this. So we start here with the surface S that has K1 as its boundary. That's the first picture up top here. Next, we need to find oriented curves that generate the homology. I've chosen gamma 1 through gamma 6, which are depicted down here in this picture. Notice they're all oriented clockwise. And I tried to give each one a different color so that it was easy to differentiate between them. Notice they do have overlap, where they do overlap on the surface, which is fine. We're going to use that for the linking number calculation next. So to calculate the Seifert matrix, it has entries linking number of gamma 1 or gamma I, gamma j plus. Plus means we are looking at the push off of that curve in the positive direction of the surface. So given the surface that we have, I choose that where we have the disc, the top of the disc that we're viewing from this angle, that's going to be the positive direction of the surface. So for example, if we look at gamma 1 and push off gamma 1 in the positive direction of the surface, is going to lift up here, lift to the right here, lift up, and then we continue this process as we go along this curve gamma 1. Once we do that and tighten it so that it looks a little nicer, we obtain this gamma 1 plus that's shown here. So once we calculate all these push-offs of our curves and then look at the linking numbers, so notice gamma 1 plus interacts with gamma 3, gamma 2, and gamma 1, so those are going to have non-zero entries in our Seifert matrix, we obtain the following matrix. This is what's known as V1. Now we don't stop there. We actually look at V1 plus V1 transpose, which notice has a very nice pattern for these last rows and columns. And now we have to figure out the sign of the eigenvalues. So if we row reduce this matrix, we obtain this diagonal matrix. Notice we have 2 negative values and 4 positive values. That implies there's going to be 2 negative eigenvalues and 4 positive eigenvalues. Hence, our signature is going to be 4 minus 2, which is 2. Now recall we wanted to show the signature as 2 times n. We have n equals 1 here, so this does satisfy the base case. In general, we would use this surface, which has Kn as its boundary. Notice I'm just introducing more bands between the 2 disks and more of the oriented curves, gammas, to find a surface with Kn as its boundary. So we have gamma 4, gamma 5. This box just designates that we're continuing this process as we move along and finish with gamma 2n plus 4. Notice they're all still oriented clockwise, and then we always have that it overlaps with its neighbor to the left and the neighbor to the right. So gamma 4 interacts with gamma 5 once and with gamma 3 once. This pattern continues as it goes across, except for the last gamma, which only interacts with the one previous. So this is the surface that we would use for the induction argument. Next, we're going to calculate the 4-ball genus. I claim that the 4-ball genus of Kn is equal to n. Like I said, we're going to use the signature to calculate the 4-ball genus. So Murasagi proved that 1/2 times the absolute value of the signature is less than or equal to the 4-ball genus. We know that 2n is the signature, so we obtain this first inequality here. If we can prove that the 4-ball genus is less than or equal to n for Kn, then we have proved the result. So this is easier to do because all we need to do is find a surface with Kn as its boundary that has 4-ball genus equal to n. So let's do it once again by using our base case first. We start with K1, and we want to create an S1 that has it as its boundary. So first of all, we're going to perform some braid isotopy first, really stretching some of these strands just to exaggerate some of these crossings. They're all still here, so notice we have 3 of the sigma ones. They're still here. There's 1, 2, and 3. They've just been exaggerated and moved a little bit. Next, we create the surface. So notice where our strands where we've now placed 3 discs. We have some twisted bands that came from our standard generators. So we have 2 here, 1 here, and then we have this very large and interesting band here in the middle. Now this band does involve ribbon intersections. Those are highlighted in green. What that means is we have our disc and our band is going to come through and pierce it transversely as it moves through. So those are what these green lines represent. So let me walk us through what this band is. So we start at the top, disc, we twist a little bit, we're pretty narrow. As we start to lengthen, we're moving around, and we end up at the back of this bottom disc. Continue to travel up, hit around halfway through the depth of this second disc. Continue to turn. Now we're even tighter or smaller, so we do not intersect the bands that we've already created so far. We do not want self-intersections. We continue to curl, move underneath, intersect this first disc again, but now farther forward or closer towards us from this viewpoint. And we continue along until we return to the second disc all along this segment here. If this is not easy to see, I have another picture for us. So same surface, I've just highlighted the discs, now red, yellow, and blue. If we're viewing this surface from the right-hand side, these discs become line segments. Here's pink, yellow, blue. I'm ignoring the twisted bands here, only looking at the orange band. So once again, walking through it, we start at the pink disc at the top and we twist. We don't really see that in this picture, but that does occur around here. We are circling around, hit the back of the blue disc. That is this piece. We start, we're moving around, hit the back of the blue disc, hit with a ribbon intersection highlighted in green. We continue to curl. That's right here. Continuing to curl, hit the yellow one somewhere close to halfway. Somewhere close to halfway, we hit this yellow disc. Continue to curl, but now we're tighter, but also getting longer, but tighter so that we don't intersect this band again. That's this piece where we're traveling along almost parallel to it as we continue to travel until we hit the blue disc again, but now farther to the front, closer to us. That green dot corresponds to this long intersection. Now we continue to travel until we join at the front of the yellow disc. So here we are traveling forward until we interact with the front of that yellow disc. So I'm hoping these two pictures demonstrate what this band really looks like so that you can see the surface that we've created with K1 as its boundary. Next, we want to calculate the four-ball genus. To do that, we calculate the Euler characteristic first. Notice that before we had 3 discs, oops, I'm going in the wrong direction, 3 discs and 4 bands. So we have this Euler characteristic calculation of -1. We know the relationship between the Euler characteristic and the four-ball genus. Therefore, we get the four-ball genus of this surface is 1, which is what we wanted to show. Now, in general, how would we change this? So we have our original surface. Recall that there's 2 twisted bands here. In general, what we do is we add 2n, we have 2n many negative bands instead of the 2 here to make a surface Sn that has Kn as its boundary. Recall that Kn is created by adding more and more negative crossings at the beginning of that braid word. Once again, we calculate the Euler characteristic. This time we get 1 minus 2n, which implies that the four-ball genus is n, which is exactly what we wanted to show. Therefore, the four-ball genus is less than or equal to n, and we have proved the result. So now that we know the four-ball genus, the last thing I want to talk about is the tau invariant. Now, using Szabo's computer program from his website, I've been able to calculate the tau invariant for the first few braids in our sequence, specifically K1 and K2, which give us -1 and -2 respectively. Therefore, I claim that the tau invariant is -n. What I need to do is find some kind of an induction argument to allow me to prove that fact. So ideas that I've had so far that I'm exploring, we have this first relationship of the tau invariant. Here, K plus means that there's a knot that has a positive crossing in it. K minus means that same knot as K plus, except at that specific positive crossing, now it's a negative crossing. So we do have this relationship which could help us proceed from one braid in our sequence to the next. The next idea is to look at grid diagrams for Kn, where we look at the element that generates the tau invariant, say for K1, and see how that element relates to the element that generates the tau invariant for K2, see if there's some relationship, some way we can generalize what that element must look like, but now in terms of grid diagrams for ease of computation. So that's my current progress for the tau invariant. All in all, here's a summary of what we've looked at so far. Recall that we have a braid sequence Kn. When we look at their closures, which are now knots, we have the self-linking number is -2n minus 1. The four-ball genus, 2 times the four-ball genus minus 1 is 2n minus 1. If we can show that the tau invariant is -n, then this first inequality becomes an equality. And by work of Plemenevskaya, we know that these two invariants, psi of k and theta hat of k, are in fact both non-zero, just like quasi-positive knots are, which shows that we have a braid sequence that just becomes more non-quasi-positive as the sequence progresses, and yet it is undetectable by these two invariants. And in particular, the two knots 12N239 and 12N512 share the fact that they are suspected to be non-quasi-positive, but maintain this equality and are unable to be detected by these these two invariants. Here is the first page of my references and the second page. And I want to thank you all for your attention and thank you for watching my talk. And I hope you have a great rest of your day and have fun at the conference.